In this short video, we will evaluate the performance of machine learning model created in Orange Data Mining using clinical data from patients with systemic lupus erythematosus. In that study, researchers measured level of inflammatory biomarkers in patients with lupus, including proteins detected in both serum and urine. One of the serious complications of lupus is lupus nephritis, which is inflammation of the kidneys. Detecting this complication early is clinically important. For this exercise, we are interested in whenever biomarkers measurement can help predict active renal disease. Importantly, in this activity, the model has already been created. Our goal is not to build the model from scratch, but to evaluate how well it performs and to critically analyze its behavior. The datasets contain clinically researched data from individual study participants. Each row represents one patient, and variables include, as you can see, for example, biomarkers measurement, patient sex, ethnicity, and information about whenever patient has active renal disease. The predictive model uses the biomarker measurement and sex as the input variables. We will see it later. Ethnicity is included in the dataset as metadata, meaning it was not used to the train model, but we can use it later to analyze how the model perform across different subgroups. Here we can see the workflow prepared in the Orange Data Mining. This workflow represents the evaluation pipeline for predictive model. So first the data set is loaded into the system, then the relevant variables are selected. The outcome we want to predict is renal disease status, while the biomarkers and sex are used as a predictive feature. The workflow includes a decision tree as the classifier, which has already been trained using these variables. Next, the model generate a prediction for the data set, and Orange calculate standard performance metrics. In addition to evaluating the model on the entire dataset, the workflow also separates the data into the different subgroups, allowing us to compare model performance across population. Let's us first look at the overall model's performance. So Orange provides several evaluation metrics. One of the most important is area under the curve. This metric measure how well the model distinguish between patient with and without renal disease. We also check sensitivity, which reflects how well the model identify patients who actually have renal disease, and specificity, which reflects how well the model correctly identify patients who don't have the disease. Overall, the model demonstrates moderate predictive performance. However, evaluating performance only on the entire dataset can sometimes hide important differences between patient groups. To explore this further, the workflow evaluate the model separately from different ethnic subgroups. The dataset contains three um, groups. A white patient, black patient, and Asian patient. The same train model is applied to each subgroup independently, and performance metrics are calculated from each group. This allows us to determine whenever the patient performs equally well across different population. When we examine the results, we observe clear differences in predictive performance across subgroups. The model tends to better in the majority subgroup, which in this data set correspond to the white patient. In contrast, the performance is lower in the minority ethnic groups, including Black and Asian patients. In some cases, the model ability to distinguish between disease or and non-disease approaches levels close to the random classification indicating weaker predictive performance. But why do these differences occur? One possible explanation is dataset imbalance. In this dataset, the majority of patients belong to the wide subgroup, while other groups are represented by fewer observation. Machine learning models learn patterns from data using during the training here. If certain groups are underrepresented, the model may learn patterns that reflect primarily the majority group. As a result, the model may generalize poorly to population that were less represented in the training data. This example illustrates important issue in the medical artificial intelligence known as algorithmic bias. Even when sensitive attributes such as ethnicity are not used as a predictive variables, model may still show different performance across subgroups. In clinical settings, such differences may lead to unequal diagnostic accuracy, which raises ethical and practical concerns.